So in order for us to talk about X-ray diffraction, we have to think about crystal structure. Okay, crystal structure. And of course, crystal structure is important. I learned this recently in a scientific video. The new influenza that Professor Sato's group is expert of, probably influenza. It is composed 1/4 of the Spain flu, 1/4 of the pig or swine flu, 1/4 of the bird flu, and 1/4. So remaining 1/4 is a type A influenza, human influenza. So it's a mixture of everything. This is why now people don't call it swine flu, because it also has a bird flu and so on. But then there's a researcher trying to make a single crystal, basically the crystal of these, protein and everything, and then trying to analyze the structure so that they can come up with some new chemical or medicine that can actually, I forgot exactly, but it was, that those guys make, ribbons and other CH structures. And then there's some binder here, then when something attached to this, that's when the flu becomes bad. So they're trying to come up with determination of this structure. Then they're trying to look for new substance that can bind here instead of the flu, so that this is deactivated. But even for this, people are trying to use X-ray diffraction to find structure of this. And Professor Nakasako's group is actually the expert in this. They're good at making single crystal. Single crystal. You have to have single crystal, but not necessarily single crystal. It can be polycrystalline, but still, you have to have crystalline, something with the periodicity, so that periodicity can be found by X-ray. And so this is why we have to think about the crystal structure first, because the crystal structure is defined as something with the periodicity of atoms, molecules, and so on. Okay? So that's one incentive to learn about crystal structure. The other, of course, importance, although I'm not going to cover in this class, let me tell you why knowing crystal structure is important. And to make the story very simple, let's just think about here being some kind of a metal rod, aluminum, gold, whatever is fine. And then I have a battery attached to it. Okay? Because it's a conductor, we have resistance R, and resistance R is given by, if I define L, the length, and the area, A, and then we have R equals to rho, R becomes long with L and small with A, right? And here, rho is known as a resistivity. Okay? So this is ohm. This is meter square. So naturally, this is ohm meter. Okay? That's the unit. So let's just think about, even for this electronic simple conductor, why the crystalline structure is important. Here I have a voltage V, so the electric field is given by V over L. electric field here. So for the moment, let's just switch off the circuit. And there are electrons in the crystal moving around. What is the driving force for the electron to move around? The energy is given by the thermal energy. So in this case, we have for E equals 0, electric field 0, we have so-called thermal energy, which is given approximately by 3½ Boltzmann constant temperature, and that gives thermal. So that gives motion of this energy is transferred to electrons. So that m is an electron mass, and v is the velocity of the electron. Okay. And with E, with the switch on, with the electric field switch on, we have F force equals to, well, some kind of vector, Q E equals to, and if this is Z, Y, or X direction. Oh, this is not so good. X should be. Oh, this is okay. This is okay. This is okay. Then we have the electric field in Y direction. So we have m d squared y d t squared. Okay? And Q, of course, is a charge. Q is a charge. So it's 1.6 times 10 to the minus 19 Coulomb. That's a Q. Okay? And in Japanese high school, I don't know how you learn in your country, but this is usually put as an A for acceleration. Okay? That's okay? Remember, I'm trying to explain to you why the crystalline structure is important. And then the acceleration A is given by F divided by m. M again is the mass of the electron. Okay? And that's from this QE, so QE, this is just a scalar. QE divided by m. And then we get, finally, we have the V thermal, but we also have, what we're trying to get is this drift velocity, V sub d, which is given by acceleration times average tau. By the way, this is velocity. So we want to have, the difference is that thermal velocity is just a random motion. Drift velocity is induced by this electric field in y direction. And tau here is defined as a average time requires for the electron to accelerate to, as a function. I only talk about one electron here, just as an example. Maybe electron gets accelerated and then hits something, gets scattered and stop. And then it is again accelerated by the bias, and then stop. Accelerated and stop. Accelerated and stop. Right? And this, each interval between scattering is called relaxation time. Relaxation time. So if I'm free, I can just run, but if I hit something, I stop. And I'm accelerated in this direction because I'm negatively charged, and there's a positive bias in this direction. Okay? So there's a relaxation time, which basically defines how accelerated and how it is stopped. And average relaxation time, average of these are defined as an average relaxation time. And that's what is shown here. That's what is shown here. Okay? So it accelerated, get to certain velocity, and then stops. And so this is approximately, some people say, hey, 1/2 is missing, but let's just say order of magnitude. This is a drift velocity. Okay, drift velocity. And then drift velocity, because A is given by this formula, QE m tau is known as a drift velocity. And then after all, this drift velocity is given by Q mu E, where mu equals Q tau m. Q tau m is known as a mobility. Mobility. So mobility is how velocity is proportional to applied electric field. If everything works out well. And then this is basically a proportional constant that determines how electrons are accelerated with externally applied electric field. Okay? So I have about 6 more lines. But before I move on, let me clarify one thing. If I plot V Z Vy and Vx, that means velocity in x, y, and z direction. The V thermal is completely isotropic. It's a random, right? So V thermal gives something sphere, right? Around the center, V thermal. And this sphere becomes large or small depending on the temperature. Okay? But V thermal is large because K is very large. Okay? This is very large. KT is about, yeah, this is very large. So, and if I compare this with drift velocity is very small. So what is happening in this bar is that electrons are moving around basically completely randomly. However, some components of the electric field adds little components of the velocity to the y direction. So it just shifts the whole randomness a little bit to the y direction. So in essence, when I applied V, what I get is very small shift of this distribution sphere to the right. This is not really a sphere here. Okay? So electrons are just moving very randomly, but small application of 2 volts or 3 volts introduces velocity shift, velocity shifts here corresponding to mu e. Okay? So far I have introduced no crystalline structures, but all of these are related to crystalline structures, as you will see soon. Finally, I'm going to talk about Ohm's law. Ohm's law. Ohm's law says V equals IR. You've seen it before, right? And then E equals to, for example, rho J, or in other words, sigma 1 over sigma J, where sigma is a conductivity, not thermal, but this is electric conductivity. And then J, of course, is the current density. So that's given by charge, number of charge over second, and millimeter square. Millimeter square. Okay, number of charges. So basically what we are talking about is that, let's say we have some kind of plane, and we have some area small area dA, and then, here the current density means how many charges are going through per unit time per unit area. Okay? And then how many charges are going through is given by per second, per unit time is given by v dt, right? Because velocity times dt is a second. Okay? So once you accept this, you get this relation here. Once you accept this, J equals to how many charges are going through per unit time and unit area, right? How many charges per unit time and unit area, and that is given by dq dt, and that is given by q and v. What's q and v? What's q n? Sorry, n is a concentration of charges or electrons then that's given by 1 over m cube, right? So basically this times this concentration of electron times charges times velocity gives current flux, and that's given by Q N mu E, because velocity is given by this, right? Mu E. And that's known as, we will usually write this sigma E, where sigma is the conductivity. Sigma is therefore Q and mu equals to Q square N tau M. So this is where I wanted to get to. So now we have reached a simple equation you know very well. Current density is proportional to the conductivity and electric field you apply. So where are the crystalline structures? Right now, we didn't use any of the information we get from crystalline structure. However, even for us to calculate conductivity is given by this one. We have to know, well, Q we know, it's a constant charge. Do we know N, concentration? No. Do we know concentration of the electron in this aluminum? No. And do we know the mobility of the electron in this aluminum? Not at this point. And we have to be able to calculate that. And in order for us to calculate this, we always start from crystalline structures. For the case of aluminum, we will reach the conclusion that each aluminum atom approximately contributes 1 electron to move around. Then we have to know the crystalline structure of the aluminum so that how many movable electrons there are within unit volume. Number of electrons per unit volume is this concentration. And then we have to see how these electrons move around. How do electrons in aluminum get accelerated? How easily do they get accelerated if we apply electric field? That's a mobility. Do we know the mobility? Well, in order for us to know mobility, we have to know the mass of the electron and how often electron hits something to get scattered. Mass of the electron, to find mass of the electron, we have to know the crystalline structures. Starting from the periodicity, we will find how electrons are, starting from the periodicity, we find average or effective electron mass. Think of it this way. If I just walk around with a constant pace, maybe I have one positive minus charge, and then there's a positive charge over there, so I get pulled, right? Coulombic force. That's okay. But then what happens if I have every 1 meter, I have some obstacle to go over. So I have to go up again, I have to go up again. I slow down, right? That's what happened in crystalline structure. In a crystalline structure, electron moves around, but every certain periodicity, you have positive charge, ions. So electron gets pulled to the plus, but then as you walk away from the positive charge, you get pulled back. So you have this constant periodic background structure that electron feels. And if you try to solve every second or every nanosecond or every picosecond of what's going on, it gets too complicated. So the smart people came up with this idea that, okay, if the periodicity is constant, we can just average them out. I get accelerated, 1 meter, another meter, I'm slowed down. So what do you do if you want to use Newton's law? Or, this kind of a structure, this kind of thing. You just change the effective mass. More periodic obstacles or higher obstacles you get, you just scale the mass. You change the mass. So you can just use the, classical Newton laws of motion. In the course of averaging out, you have to use quantum mechanics. But at the end, you give electrons in aluminum certain mass. You give electrons in iron different mass. You give electrons in silicon different mass, so that we can always use this relation. Okay? Because this is not interested, well, some people are interested in this, but because I promised that we will work on NMR, I will not cover this, but in this course. But the point is that crystalline structure determines even the mass, average effective mass of electrons in solid. So this is why people always start from crystalline structures. The scattering too, this tau, scattering is also determined to a certain extent by periodicity of the atom. What is the periodicity? What is the cause of the scattering? One of the major scattering cause or mechanism is by atomic vibration in aluminum, or vibration of atoms. I say, because these atoms are not moving, I assume static non-movable periodicity to begin with. Because nothing's moving, if I were an electron moving around, I just feel constant and periodic 1 meter apart or 1 nanometer apart atoms that I can average out. But in reality, these atomic positions are moving by thermal vibration. And this displacement from where it's supposed to be actually confused me to average them out. So I know I can, if I were an electron knowing exact crystalline structure, I can just close my eyes, every 1 nanometer, I just, raise my foot to go over. But if they're moving, of course I get, hit before I encounter atom and stop. That's how scattering occurs, right? And these lattice vibration again is a function of the crystalline structure, because it's just in a simple-minded picture, it's a ball of mass m connected with a spring, right? But one atom with a spring, so they vibrate. And you've solved this before, probably. You know that you get different vibrational mode. But this vibration mode is a function of the distance between them, spring constant, and the mass of the atom. Again, you have to know the crystalline structure. So this is why, even to find out tau, how often electron gets stopped, you have to know the crystalline structure. Okay? And concentration is very important. You have to know the concentration. If I said approximately there's 1 electron per aluminum atom, but how do I come up with this conclusion that there's 1 electron per atom that contributes to the conduction? This one I know from calculation of the effective mass, and then calculation of periodicity, and then I find out how electrons, all these electrons available, are placed from the lower energy to the higher energy. And then at some point I ran out of electrons to pack. I put electrons from low energy to high energy because no 2 electrons can take same energy. Remember? Electrons have to take different energy. They are Fermi particles. So, you put them. And then you pack electron up to a certain level, and then you have to know then how electron can move. Okay? So, again, to do this, you need to know the idea of the electron lattice periodicity. So, crystalline structure determines almost everything. Not everything, but it determines a lot of things. So then the easiest starting point to find what the crystalline structure is by X-ray diffraction. So this is now I'm going to move on to the description of crystalline structure and X-ray diffraction. What time is it now? How far did I speak? Only 40 minutes? Okay. This is only 1/4 of the course. Let's take a 5 minutes break because it's just too much for both of us. I want to go get some water. There are 2 things. It's a real space and reciprocal space. So, real space is where we live. Reciprocal space is what, as a result of Fourier transformation of the real space. Okay? And this is what you observe using X-ray. You observe reciprocal space. Well, we do Fourier transformation because you see if you are sitting periodically, right? You have wavelengths. One, you have some periodicity sitting apart. And if I Fourier transform it, I just have some kind of a characteristic lattice constants, distance between each of you. And just, basically the Fourier transformation of the sine wave from infinite to negative infinity is just 1 point, right? Fourier transformation. So basically, we assume crystal with infinite size, and then we have, within the crystal, we have periodic atomic sites, which we consider as if it's a wave. And then, if we Fourier transform it, we just get 1 point. So make the whole thing into just conversion into 1 point. And this is what you see as 1 point in an X-ray diffraction. So this is simple as that. In other words, if you are atoms and you emit X-rays 360 degrees all over you, you are emitting X-ray, and so on. And then let's say you are packed in a periodic way. At some point, all of the X-ray emitted from you, X-ray emitted from you, and so on, at some point in the space, construct, I should say, not diffract, interfere constructively. So the wave coming from you, wave coming from you, wave coming from you, they all have large amplitude, so that intensity at 1 point in the space becomes very large, right? And then once I know here is a point where I get strong intensity, then I know, then also if I know the wavelength everybody is emitting, then I can find out, okay, you, everybody is probably in the distance that are multiple of integers of the wavelength, right? So this way I can find out where each of you are. So this is how we try to look between real space and the reciprocal space. But the constructively interference point is actually point in the reciprocal space. That is reciprocal space overlapping with the real space. So it gets complicated, but you'll find how everything is put all together. Okay. So now I write simple crystalline structure. I'm drawing two-dimensional crystalline structure. And I think I say this is crystal because I can define one vector this way, the other vector this way, and everything in this lattice point is given by using this vector. I say this is vector, okay? A1, and this vector is A2, and then here I define this is in a three-dimensional space I get A1 plus and plus 2 okay, these are vectors. And I say A1, A2, A3, are primitive vectors. And N1, N2, N3 are 0, plus minus 1, plus minus 2, plus minus 3, and so on. So let me start with 2 dimensions. The crystal that has periodicity is defined as the following. In a 2-dimension, we should be able to define 2 primitive vectors that allows to find describe every lattice point as a sum, vector sum, containing integers in front of these primitive vectors. So if I want to describe this particular point, this is 2a1 plus, so this vector here, this r vector here is 2a1 plus 1a2, right? Right? And doing so, I can find atoms in every point. So this lattice has to be infinitely large. Okay? And this type of structure is known as a Bravais lattice. Bravais lattice. Okay? So now the question is, this kind of a honeycomb lattice Bravais lattice? Is this Bravais lattice? Yes or no? Answer is yes or no. Is this Bravais lattice? Yes? No? No votes? No votes? Yes? Yes? Okay, 2 yes, 3 yes. Now how many no's? 1? 3 no's. And 1 forfeit. No. It's no because if I choose these vectors as the primitive vectors, this plus this is here. And an atom is missing. So even though this seems to have periodicity, yes, it does have periodicity, but it does not qualify as a Bravais lattice because one atom is missing. Right? And this of course this is the case for many protein structures. I mean, things get even more complicated in the protein structures. So what people do is group them, for example, group these two together, group them together, for example, as if the pair is composing one atom or one molecule. Then all of a sudden the pink cigar forms Bravais lattice. Right? Now Now I can say, I can define this as two primitive vector, A1 and A2, and I can represent the position of every cigar using integer multiple sum of these A1 and A2. Okay? And what protein people works is even more complicated. Right? They group this and this together, 4 of them together, or 5 of them together to have some periodicity, and even, group 5 of these 5 atoms together to find another periodicity and so on. It's a big puzzle. But we will get to this later, the simple example, but not for the time being. Okay? So let me show you how we work in real space. 3D, 3-dimensional single crystal. We have atom. This is a simple cubic lattice. And very often we say, for example, for this case, let's just say this is Z direction. Let's just say this is Y direction, Y, and this is X direction. Yeah, let's just say X, Y, Z. And in this case, if I define this as A1 and this as A2 and this this as A3, then A1 is AX, A2 is AY, A3 is AZ. A is the distance here, X, Y, Z is a vector of the length unity length 1 in X, Y, Z directions, respectively. Okay. So now this is scalar, and this is just a vector of X direction of the length unity, length 1. Okay. Now things will become a little bit more challenging. Maybe it's a better idea for me to show you professionally drawn structure rather than me trying to show you what it is, but you understand, right? Now I'm going to draw somewhere in the middle. There's a ball. It's a body centered cubic lattice. In short, we always call it BCC. Okay? body-centered cubic lattice. So what is the reciprocal lattice vector? Oh, sorry, the primitive vectors? There are many different ways. If I want to just do it very simply, maybe I choose this. Let me replace this one a little bit to somewhere. This, and somewhere in the middle we have one more. So and this is again Z, X, Y. So A1 is AX, A2 is AY, A3 is A over 2, X, okay? And you'll find later that even though this seems to be a very straightforward choice or natural choice of selecting A1, A2, and A1, A2, and A3, there's actually a better way of choosing A1, A2, and A3 because they are not very symmetrical. When you want to make calculation, you want to make them more symmetrical. So you make one calculation for A1, and then you don't have to do this for A2, A3, and A4. Sorry, not A4, A3. Okay? So better choice is the following. Here you have to see to understand what I'm doing. I choose, let's see. Okay, I choose one of them here to the center. Okay? I choose the other one. There's another one in the bottom center, right? There's another atom in the bottom center of the bottom qubit. So I choose this one. Okay? Then I choose the other one as a then I say there's another atom in the center of the box in the direction minus y, right? So I choose another atom here. Hope you see what I'm doing. This is now very messy, but if I choose vector like that, then I get A1 equals to A over 2. Let's say Y plus Z minus X. So where is this? Minus X. I don't have minus X in this. I don't have minus X here. Do I have minus X? No, I don't. I have to redefine something to the minus X. Y, Z, minus X. So I have to choose, well, this is, I have to choose, I have to put, I have to add another box and choose atom center of here. Sorry, right? So this is, now this vector is this. Y, Z, minus X. Is that okay? So this is A1. This is A1. A2, A over 2, Z plus X minus Y. Maybe I have to redraw everything. Z plus X minus Y. Oh. Z plus Y. No, that's no good. Minus Y, so the other way around. Unfortunate. Now I have to redraw everything again. But do you see what I'm doing? You see what I'm doing? I don't have to draw anything anymore if you know what I'm doing. What is it?
Isn't it the one at the top? Like Z and X and minus Y. It's the one at the top you choose.
Z and oh yeah, that's right. One at the top. This one. Yeah, this one. This one is A2. Right. Thank you. Thank you. So this is A2. A2. And then A3. A over 2. X plus Y minus Z. X plus Y minus Z, this one, A3. This is A3. Okay? So this way you can see A1, A2, A3 has same symmetry, same equations, but different components. So it is easier for you to use this one in a calculation of the reciprocal lattice you are going to perform perform shortly. Okay. And to make the story complete, let me just draw one more thing. FCC, face-centered cubic. And this has then here I'm going to choose this one here and this one here and one on the bottom. This one here. I still have to define Z, Y, X, and A1. In this case, A1 is given by A over 2, Y plus Z, A2, A over 2, Z plus X, A3, A over 2, X. So Y plus Z, Y plus Z. So this one is A1. Then Z plus X, Z plus X. So this is A2, this is A2, and this is A3. Okay? A3. Okay, so I don't think you're going to. Yeah? Yeah?
Is that A over 2 square? 2 square root?
2 square root? Here, for example, A1. A1 is this plus this is this divided by 2.
So A is not...
A is this distance here. A is always distance here.
So we have 2 square root of 2.
Oh, no. You see y, ay, this is ay, right? And this is az, right? So I say ay plus ay, az plus ay gives vector from here to here, right? Divided by 2 is this one.
Okay.
Yeah? Yeah, divided by 2 is the yeah, okay? That's fine. So so that's the idea. Okay? And later I will introduce diamond lattice, but not for the time being. Okay? So I just want to move on. I think we move on to the reciprocal lattice, because otherwise I will never get to the X-ray diffraction. So now we have defined the real lattice in terms of the periodicity, and we use a new term called Bravais lattice. Now I go to the reciprocal lattice. What is reciprocal lattice? Reciprocal lattice. Reciprocal lattice is defined as a collection of plane wave that have periodicity of, or periodicities. Maybe I should put this plural. Of the Bravais lattice. So I will put down the equation first, definition. Then I will show you graphically what I mean. Okay? So I put down plane wave E I K. It's a vector R plus equals to E exponential I K dot R. This means definition is given by E I K dot R equals to 1. Okay? Let me just tell you what we have here. K is a reciprocal lattice vectors. I will show you what it is. R is just a vector, arbitrary vector in real space. Okay? Large R is a translational vector between Bravais lattice. Remember, I defined already. Large R is given by vector A1, A2, A sub 3 with, multiple additive of the numbers. Okay? And then what I'm saying is that here, any arbitrary vector plus translational vector is same as this, as if it's not really translated. So naturally, to meet this condition, to fulfill this condition, you have to have exponential I K dot R equals to 1. Okay, that's the condition. And this is a definition of the reciprocal lattice. So now I'm going to show you what it is graphically. I just draw simple cubic lattice. Simple cubic lattice. Okay? And we have atom. And so on. Okay? Now, so we have atom here. Now, what is the plane wave that has periodicity of the lattice, Bravais lattice? I will show you one example. One example is the following. Here is the periodicity of the Bravais lattice. I put one wave like this. Wave, right? Wave having the wavelength A. This is A. This is A. This is A. And this has a periodicity of the lattice, right? Because if I translate this wave by R, given by, let's say this is Y direction, this is X direction, and this is Z direction. I translate this by A2, Y direction. Then what I get is this following. Right? And I translate this by 2A. 2A2. And what I get is this wave. So this particular wave having wavelength A, this wavelength A, lambda equals A, lambda 1 equals A, has the periodicity of the Bravais lattice. Okay? Any other waves that have periodicity of the lattice? Do you think this is the only one? No. In fact, there are infinite number of waves. Do you understand? Because you can put two of them here, right? Then they form periodic. This wave has periodicity of the lattice, right? This particular case, lambda 2 is A over 2. You can put even more. I mean, you can go on forever. You can go on forever. You can go on lambda 3 equals A over 3. A over 3, right? And so on. You can go on forever. And then, important thing here is that there's a relation that lambda equals 2 pi k. Lambda is a wavelength. K is known as a wave number when it's scalar. And when k is vector, it's called wave vector. Wave vector, okay? So, for this, we have how should I do this? Let me think. Lambda equals to 2 pi k. Let's just write down 2 pi k1. Okay. And then this is 1 over 2, 2 pi k1, right? And this is and so on. Make sense? So now, only for y direction though, we have found k wave vector for the plane wave that has periodicity of the real lattice. Remember, I said reciprocal lattice is a collection of plane waves that have periodicity of the Bravais lattice. And to be more precise, it's a collection of k of vector of Bravais lattice plane waves that has periodicity of the Bravais lattice. So in this particular y direction, I have now I'm going to put I will make a huge transition from the real space to the reciprocal space. Suddenly I draw axis KZ, KY, and KX and KY. Okay? Suddenly. In Y direction, we have 1 K1. Right? So I have, starting from origin, we have points at K1 in Y direction. Right? The next one is here, 2K1. So we have another one here, 2K1. We have another point, 3K1. So we have 3K1. And in fact, it goes on forever. And I can go to the other direction too. We have this point, this point, this point, minus K1, minus K2, minus K3, and so on forever. Okay? We can do the same thing in X direction, right? I can find waves in X direction. In fact, we're going to find the same thing. K1, distance-wise. K2, 2K1, distance-wise. And then Z direction is the same. And it's the same in this direction. Right? And all of a sudden, I can fill in, for example, this plus this gives another point here. That's another periodicity of lattice. So I can construct just from K, I find from the periodicity of the lattice, I can construct very similar lattice points in a reciprocal space. Okay? And we call this, for example, this vector B1, this vector B2, this vector B3, and this forms Bravais lattice. B1, B2, B3 is a primitive vector, and large K is the lattice which gets N1. I've already used N. And so on. Okay? Oh, by the way, of course, this is, oh yeah, I've already drawn. I erased it. This is Y, this is X, this is Z in a real space. So now, I have real space and reciprocal space. And what is interesting is that real space X is the same direction as reciprocal space Kx. Real space Y is same direction as, or parallel with reciprocal space Ky, K sub Y. Okay, so let me stop here, take a 10 minutes break, and then I will move on with actual manipulation or finding relation between real space and reciprocal space. Okay? So now, basically, even for body-centric cubic, BCC, or for FCC, face-centric cubic, you can look at it by inspections. By inspection, you should be able to find, okay, in this direction, this is the wave having the periodicity of the Bravais lattice, and you can put one point in reciprocal space, the other point in reciprocal space, and so on, and you can just move on with that. However, there is very convenient formula which which gives you the relation between reciprocal space and the real space. By the way, this is cross. This is dot. So this is inner product, and this is outer product. Okay? And of course, our real space vector is given by n1 a1, n2 a2 plus n3 a3. Reciprocal lattice vector is given by maybe I should use K. K1 B1 K2 B2 K3 B3. Okay? So let's try the simplest example. What is so for simple cubic? Simple cubic structure. Simple cubic structure. We know A1 is AX, B1, A2 is AY, A3 is AZ. We also know already that K, what was K? Something like 2 pi over A, right? So we actually know that B1 equals to 2 pi over A X, B2 2 pi over A Y, sorry, that's X, B3 Do you agree? Do you agree? Remember, this is, in B direction, we have K1, 2K1. And K is given by, A is 2 pi over K, it was lambda, right? So K1 is 2 pi over A, right? So 2 pi over A in X direction, it was a reciprocal lattice B1. So we know the answer already, but let's just put these relation into one of the formula and see whether it works. So, to find B1, we have to have 2 pi over A cross. So we have to do A2, A3. What is A? We just have to do y, z makes what? yz makes plus x, right? So this becomes but let me just move on. And then this is what? This is A1. So AX dot A2 times, it's the same thing. AY okay? So that is 2 pi over A square x, right? And then this is AX A square x. Okay? This is okay? And this is inner product. So x, length of this x is 1, right? Basically, this equals to 1. By the way, of course, x, y is 0. Anything different is 0, different. So, this is 2 pi over a square x a cube a, which is 2 pi over a x. So same as this one. Okay? Square. Okay. Okay? So this one seems to work. This equation seems to work. So for this, I would like you to spend some time now to work on body-centered cubic. Okay? So you think you can apply. I have already given you A1, A2, and A3. Right? For body-centered cubic. Don't use the asymmetric one. Use the symmetric one. Then this way you know. You only have to work on B1. Once you know B1, you can find B2 and B3. Okay?